Hi guys, this is another past paper walkthrough. It's not mentioned anywhere. I mean, if you spot it, let me know. But this is from January of 2023, and it's Unit 4. Okay, so let's just start. Okay, so Section A, Question 1, and I will repeat it for the billionth time, but usually. The amount of marks a question gets is the amount of time you should spend on a problem. So a 1 mark question should take you about 1 minute. Okay, some questions will be more difficult, so you will need more time and so on, but that's a good rule of thumb because you have 1 hour and 45 minutes for these papers. So question 1. The table shows the charges of up and down quarks. Okay, which of the table shows the quark structure of protons and neutrons? You have to remember that protons and neutrons are baryons, and baryons have 3 quarks. So C is the right answer because a proton has two up quarks. So their charge is 4/3 minus 1/3 for the down. You get a charge of 1. Whereas for the neutron, 2 downs have a charge of minus 2/3, which cancels with the up quark that has a charge of plus 2/3 for a total of 0. Okay. Question 2. A laboratory centrifuge rotates at 1500 revolutions per minute. Which of the following expressions gives the angular velocity in radians per second? Okay, so this is kind of simple. Omega is given by 2 pi times the frequency, and here the frequency is given in terms of revolutions per minute. So you have 2 pi times 1500 revolutions per minute, and 1 minute, you have to remember that is 1 minute is 60 seconds. Therefore, let's read it off. It's D. Yes, yeah, D is the answer. Okay. Question 3. A nucleus of element X emits an alpha particle to produce the nucleus Y, 23391. Which of the following is the correct nucleon structure of element X? So you have X going into Y, 23191 plus alpha and an alpha particle. You have to remember that has a charge of 2 and a mass number of 4. So you have to add these mass numbers up. So 235. And if you add the charges, you get 93. So, okay, they ask for neutrons and protons. Okay, so the answer is either B or C. So 93. Wait, something's bothering me. It's 233. I'm sorry, guys. Okay, so this is 237. Okay, so the right answer is B. I'm sorry, I didn't read this, so I thought it was 231. Okay, question 4. The diagram shows the track of a charged particle in a magnetic field. The magnetic field is directed into the page, so it's like that. Okay, B. Which of the following particles could create this track? Let's see. So you have to use Fleming's left-hand rule, and your index finger should point in the direction of B. If okay, and then let me think. So a muon traveling from X to Y, a positron traveling from Y to X, a pi plus traveling from X to Y. Okay, let me think. The answer is D, I think, but let me verify. So index finger in the direction of B. So your index finger should point into the page, and then your thumb points in the direction of the velocity. Okay. In case you are talking about a positive charge, otherwise your thumb should point in the opposite direction. So yes, okay. So if it's an electron, it experiences a force that it's inwards, right? So the force is like that for the electron. So it has to be traveling this way, okay? Because if you put your index in the direction of B and your thumb in the opposite direction than the velocity is this way, so your thumb should point in this way. Therefore, the force experience is inwards, okay? So the answer is D. I hope this makes sense. It's difficult to explain using a screen because you can't really show your fingers and your method. So anyway, question 5. Which of the following statements is not a valid conclusion from alpha particle scattering experiments? All right. Most of the atom is empty space. That's actually a conclusion from this experiment. So let's move on. Most of the mass of the atom is concentrated in the nucleus. That's another conclusion. So we have to move on. The nucleus contains all of the charge of the atom. This looks promising. The radius of the nucleus is very small compared to the radius of the atom. So, C, because the nucleus does not contain all of the charge, you have the electron cloud as well. So I guess C is the right answer. So, question 6. Point charges of equal magnitude are placed close together as shown. Which of the following diagrams shows the electric field around the charges? Okay. Remember, electric field lines go from positive to negative. So they look like this. And then you have lines coming out from this side and coming into the negative charge. So the answer is B, okay? All right, question 7. Which of the following statements is true for a cyclotron? A cyclotron can be used to accelerate neutrons. That's totally false. A cyclotron uses a magnetic field to increase the speed of particles. Magnetic fields cannot increase the speed of particles. They can only bend their direction of motion. So that's wrong. Option C, a cyclotron uses an alternating potential difference at a constant frequency, which is true. So let's see if this is wrong. A cyclotron uses an electric field to keep particles moving in a circular path. That's false, because the electric field accelerates the particle. It doesn't make them go in a circular path. Question 8. A non-relativistic particle of mass m has momentum p and kinetic energy ek. A second non-relativistic particle of mass m over 2 has momentum 2p. Which of the following expressions gives the kinetic energy of the second particle? So the way I work these problems out is to start with ek that is given. Okay, so ek is p squared over 2m. You have to use that expression for the kinetic energy because it's simpler. Therefore, ek prime for the second particle is going to be 2p squared over 2 times m over 2, right? And I took 2 to the numerator. So let me think. So we have 2 squared, which is 4 times 2. We have 8p squared over 2m, right? Which is 8 ek. So the new kinetic energy is D. I hope this makes sense. All right, question 9. A ball traveling at speed u towards a wall collides with the wall at right angles. The ball bounces off the wall at speed v in the opposite direction. So this is the situation. You have the ball speeding onto the wall and then getting bounced off the wall, moving to the left. So something like this. Okay. The time for the collision is t. Which of the following expression gives the average force on the wall during the collision? Okay, so let me think. So we have to use the impulse formula. So the impulse is force times delta t, and force times delta t is equal to delta p. Okay, so the force is delta p over delta t. So the mass of the ball is m. Okay, and then we have delta v. So m delta v over delta t. So we have m over delta t, and then we have to subtract the final velocity, which is minus v, and then minus u. Okay, so the answer is minus m u plus v over t, but this is the change. So this is the force experienced by the ball. Okay, the force experienced by the wall is the opposite of this, so the answer is actually A. Okay, I hope this makes sense. It's kind of weird. It's a weird question, but okay, I hope this makes sense. So the reason why these velocities are negative is because the final velocity is v, but it's to the left, so I have to use the negative sign. And then the initial you have to subtract the initial velocity, so that's why you get the minus sign there. But you have to recognize that this is the change. This is the force experienced by the ball. Okay, so the wall experiences an equal and opposite force in the opposite direction, so the answer is A. All right, this is a difficult paper already. So let's go to question 10. A proton is accelerated by a uniform electric field. After time t, the speed of the proton has increased by delta v. A helium nucleus is accelerated by the same electric field. After what time will the helium nucleus achieve the same change in speed? Okay, so acceleration is given by change in velocity over time. So delta t is delta v over a. Okay, but you have to recognize that for a proton in an electric field, E experiences a force E times the electric field, and this should be equal to m times a. So you can substitute the expression for A into there. So delta t for the proton is going to be, let me think, m delta v over E times E. Let me use a clean page, okay? So delta v for the proton is E times delta t over m. Okay, for helium-4 now, helium-4 has two charges, so the force it experiences 2 times E times the electric field, and this should be equal to its mass, which is 4 times m times A. And here we assume that the proton and a neutron are have about the same mass. Okay, so the acceleration for the helium-4 nucleus is E times E over 2m. So delta V is E, so delta V prime, say, okay, it's going to be E times delta T prime over 2m. But these two guys have to be the same. We have to set them equal to see what's different. So E times delta T over m, which is delta V for the proton, should be equal to E times delta T prime over 2m, which is delta V prime for the helium-4 nucleus. So this goes away, this goes away. So delta T prime is 2 times delta T, okay? So the answer is B, okay? Okay, I already said it, this is a difficult paper, so let's move on. Okay, section B. A muon will decay into a neutrino, an antineutrino, and an electron, or a positron. A positron is the antiparticle of an electron. State one difference between a positron and an electron. So they have an opposite charge, okay? So they have opposite, oops, my handwriting is horrible, I'm sorry. So they have opposite charges. And specifically the electron has a charge of minus E and the positron has a charge of plus E. Question B. Explain whether the following decay would be possible. You should consider conservation of charge and lepton number. Okay, so we have mu minus, so a negative muon decaying into an electron plus an electron neutrino plus a muon antineutrino. So the charge on the left hand side is -1 and it's -1 on the left hand side. Okay, that's okay. Then the lepton number should be conserved. The lepton number is 1 on the left hand side, and on the right hand side we have 1 for the electron plus 1 for the electron neutrino minus 1 for the muon antineutrino, so plus 1. So lepton number is conserved, and then baryon number is conserved but doesn't really apply here because we are not dealing with baryons. But in any case, the baryon number is 0 before and 0 after because you have no baryons involved. Okay, so all conservation numbers. Oh wait, it is specified that you should consider conservation of charge and lepton number. So this is unnecessary. So all actually we have to say that this is allowed. Okay, since charge and lepton numbers are conserved. So let's move on to question 12. So a point charge is placed at point X as shown. Add lines to the diagram to show equipotentials at intervals of equal potential difference. Okay. So let me see. So it's a point charge. Okay. At intervals of equal potential difference. Okay. So equipotentials for point charges look like circles. Okay. So if this is the first circle, actually let me make it smaller so I have space. So let's say that this is your first equipotential, and let's say that this is the second equipotential, and let's say that the difference in potential between this equipotential and this one is delta V. Then the next one that will have also a delta V difference will grow apart, as they say. Okay, so something like this. Okay, I hope it makes sense. So the point is that you have to remember that equipotentials grow apart in the sense that the same change in potential requires a larger change in radius, in distance. Okay, so the distance between equipotentials grows larger and larger as we move away from the charge. Okay, I hope this makes sense. So what I'm trying to say is that if this distance is 1 meter, then maybe this distance is 10 meters, and then maybe this distance is 100 meters. Okay, but they don't give us numbers, so we don't know. So let's go to B. A charge of minus 4.5 nanocoulombs is placed 4 centimeters from X. Okay. Calculate the magnitude of the force acting on this charge due to the charge at X. Okay, and they give us the charge at X. Sorry, it took me a moment to understand that actually this charge was given, because I was like, okay, how on earth are we going to calculate that? So, okay. So the force is given by Coulomb's law, K, Q1, Q2 over R squared. So this is a problem in which we just plug in numbers. K is 8.99 times 10 to the 9. Q1, we have to convert into coulombs. Q1 is 7 times 10 to the negative 9. Q2 is minus 4.5 times 10 to the negative 9. And the distance squared is 4 times 10 to the negative 2 squared. Okay, so the force is minus 1.77 times 10 to the negative 4 newtons, newtons, but because they ask for the magnitude, we just take the positive. So 1.77 times 10 to the negative 4 newtons. Question C. The minus 4.5 nanocoulombs charge is moved from a distance of 4 centimeters from X to a distance of 9 centimeters from X. Calculate the work done on the minus 4.5 charge. Okay. So we pretty much have to calculate the we have to calculate the electric potential at position 1 due to the charge at X, which is given by K QX over R1, and then the potential at the second position, the 9 centimeter positions, due to the charge at X at position R2. Okay, so if we plug in numbers, we find 8.99 times 10 to the 9 times 7 times 10 to the negative 9 over 4 times 10 to the negative 2, and this is 1573.25 volts. And for the second position, if we plug in numbers again, the numerator is the same, but the denominator reflects the change in position. So 9 times 10 to the negative 2 gives us 699.22 volts. But we are not done yet, because we have to calculate the work done, which is given by Q. And now Q is the Q of this charge, okay, times delta V. Okay, so the charge is minus 4 times 5 times 10 to the negative 9 coulombs times the final potential, which is this, so 699.22 minus the initial potential, which is minus 1572.25, and if you multiply everything together, you get 3.93 times 10 to the negative 6 joules. Okay, let's move on to question 13. So there are 4 forces acting on an aeroplane in flight as shown: lift, weight, drag, and thrust. The lift force is perpendicular to the wings, okay. To change direction, the aeroplane banks so that one wing is lower than the other. The lift force is then no longer vertical. The aeroplane flies in a horizontal circular path at a speed of 52 meters per second. The diagram below shows the aeroplane banking at an angle of 20 degrees to the horizontal. Show that the radius of the circular path is about 800 meters, and they give you the mass of the aeroplane and the speed, which is different from the other speed for some reason. So anyway, okay, so let's analyze the forces. First of all, the aeroplane undergoes a circular motion that kind of points into the page, so it looks like this. Okay, so it needs a force in this direction, okay, which prompts us to analyze the lift in the directions that I'm about to show. So let me erase this. So what I'm trying to say is that, okay, the lift is given. The weight of the plane is always downwards. Therefore, we need a force to balance this weight. So the proper way to analyze these forces is this way, okay? Because as I mentioned, we need a force that plays the role of the centripetal force for circular motion, and that force is this component of the lift force. So we analyze the lift into these two components, okay? So if this angle is 20 degrees, then since this line is perpendicular to this line, and then this line is perpendicular to this line, okay, then the inscribed angle, which is this one, should be equal to that one, okay? I hope this makes sense. So actually, I'm gonna erase the red lines and just claim that this angle is 20 degrees, okay? And this is just from the geometry. Therefore, this component is gonna be L cosine 20 degrees, and this component, I don't know why this happened, is going to be L sine 20 degrees, okay? And the L sine 20 degrees plays the role of the centripetal force. Okay, so L sine 20 degrees is going to be mv squared over r, in other words, right? And then L cosine 20 degrees will cancel the weight. So it's going to be m times g. Okay, and how do we know that the weight is cancelled? Because the aeroplane just moves in a horizontal circle. It doesn't move up, okay? Therefore, in the vertical direction, there are no forces, okay? That's why we analyze the lift in this fashion, to cancel the weight and to also provide us with this component that is that plays the role of the centripetal force, so that the plane undergoes a circular motion as follows, okay? So, okay, the lift is not given, so using this equation we can divide them and get rid of the lift. So sine over cos gives you a tangent, right, from basic trigonometry. The mass gets cancelled, so we get v squared over r, let me think, rg, okay? And this is what I did, mv squared over r divided by mg over 1 gets this one cancelled, so you have v squared over r g, okay? I hope this is clear. And we are asked to find the radius, so the radius is v squared over g and then the tangent of 20 degrees. So the radius is 54 squared over 9.81 times 0.36, which is the tangent of 20. So the radius is 16.68 meters, which is about 800 meters as stated. Okay, that's a good start. Let's move on to part 2. Determine the time taken by the plane to move through 90 degrees of the circular path. Okay, so if we have a circle, let me draw it over here, and then I'm gonna delete it. So if we have a circle, okay, it takes, okay, let's say that you undergo one revolution from x back to x. That takes you time of 1 period. For 90 degrees though, it takes you a time of a period over 4, a quarter of a period, okay? I hope this is clear. So this is the time we will need. So first of all, let's write down the relationship between the speed and the angular speed, which is omega times r, and the radius is this radius we calculated earlier. Okay, so v is can also be written as 2 pi over the period times r. So the period is simply 2 pi r over v. So the period is 2 pi times 816.68 over 54, which is the velocity. So the period for one revolution is 95.03 seconds. So for a quarter of a revolution, so t over 4 is going to be 237.6 seconds, which is about 238 seconds. Or if you will, it's close to 240 seconds, which is 4 minutes, right? Wait, something's wrong. No, sorry. What am I saying? Sorry, guys, I made a mistake. So t over 4 is, it cannot be larger than t. So if t is 95, then t over 4 is 23.76 seconds, okay? So about 24 seconds. I'm sorry. Right. Part B. The wings of the aeroplane are now leveled as shown below. The speed and the magnitude of the lift force remain the same. Explain what will happen to the vertical motion of the aeroplane. The speed and the magnitude of the lift force. Okay, the magnitude of the lift force remains the same. Okay, so I'm going to write a few things. So when v is 54 meters per second, and the plane banks, there is no vertical motion, as we agreed earlier, okay? Okay. Hence, L times 20 times cosine of 20 degrees is m times g. So I'm pretty much reusing this relationship, okay? Let me think. Is this going to help? Okay. Okay. So the lift is therefore 1200 kilograms, which is the mass of the airplane given, okay, times 9.81 over the cosine of 20 degrees. So the lift itself, okay, assuming that the magnitude remains the same, the lift itself is 12,528 newtons, okay? So this is the lift force, but m times g is 1200 times 9.81, which is 11,772 newtons. Therefore, since the lift is larger than m times g, there will be an upwards motion, an upwards resultant force of which is equal to 756 Newton, that will accelerate the plane upwards. Okay, and this is the answer. Let's move on. Question 14. A student used a spreadsheet to model the conservation of momentum. State the principle of conservation of momentum. So, in the absence of external forces, momentum is conserved during a collision. Okay. The spreadsheet modeled an elastic collision between object A and object B. Okay. And they show us a scheme here, which is not to scale. The spreadsheet shows the initial values and final values when the student tested the model. So they have the initial values and the final values, okay, for the masses, which remain the same, okay, the magnitude of the velocity and the angle, okay. Deduce whether the values show, an elastic collision. So the kinetic energy before is going to be 1/2 the mass of object A, because only this guy has momentum, okay, times the velocity of A squared, okay, and this is equal to 0.72 joules. The kinetic energy after is 1/2 the mass of A times VA prime squared plus 1/2 the mass of B times VB. Let's also call it prime, even though VB before the collision is 0. We will use the accent just to specify that this is the speed after the collision, okay? If you add these two, you find 0.66 joules. Okay, the percentage difference between these two values is 0.72 minus 0.66 over 0.72 times 100. This is 8.3% of difference. So let's say it's not conserved. I mean, if the kinetic energy after was 0.71 joules, then you will be able to say, okay, that momentum is conserved, but with this large of a difference, let's say, is not conserved, okay? And a common problem that students encounter during working out collision problems is that when they use the kinetic energy formulas, they sometimes analyze the velocities into components, which is totally wrong, okay? Because energy is a scalar quantity, so you just need to use the magnitude of the velocity. You need the components of the velocity when you deal with momentum, which is a vector quantity, okay? So let's go to part 2. Deduce whether the values show the conservation of momentum. So this is what I'm talking about. Now we need to use two separate axes. So in the x-axis, the momentum before in the x-axis is simply ma times va, okay, because this guy just moves in the x-axis. So that's simple. So multiplying the quantities gives us 1.11 kilograms times meters over seconds. The momentum after, so the momentum after the collision in the x direction is now, we will need ma va times the cosine of this angle, which is given. So angle of velocity to x direction. Okay, so this is theta, and also we'll need mb vb times cosine of theta. Let's call this theta 1 and let's call this theta 2. Okay, I hope this makes sense. So we will have ma va prime cosine of this angle pretty much, which is 54.5 plus mb vb prime cosine of The other angle is minus 48, and it's minus 48 because it's on the negative side of the x-axis. Okay, so it's in the negative direction. I mean, it goes clockwise, as they say. Okay, so this gives us 1.1 kilograms meters per second. So in the x direction, we have a conservation of momentum. Now, let me use this color, and now we have to find the momentum before in the y direction, okay, which is just 0, right? Because before the collision, nothing moves in this direction, okay? So the momentum before is 0. Therefore, the momentum after, so this component of the momentum and this component of the momentum of the two objects after the collision must be equal, okay? Pretty much. So P after in the y direction is MA VA prime sine of 54.5 plus MB VB prime sine of negative 48. And if you sum this up, you find 0. Okay, so momentum is conserved. So it's all good with the world, I guess, and physics. So let's move on. Question 15. All right. A student placed 2 magnets on a holder so that the north pole of one magnet faced the south pole of the other magnet. The arrangement was placed on a sensitive balance calibrated to measure force. The student held part of a closed loop of wire between the magnets as shown in the photograph. Okay. When the student moved the wire quickly downwards between the magnets, the reading on the balance changed. Explain how the reading on the balance changed. Okay, so this is a long writing problem specified by this asterisk over here, which means long writing. So let's start writing down some thoughts. So the magnetic field yes, the magnetic field B is between the magnets is constant. Okay, when the wire, so I'm trying to find, okay, let me use a clean page to draw a scheme of what's going on. So the situation is something like, looks something like this. So, okay, so let's say that this is the north pole of the magnet, and let's say that this is the south pole of the magnet. Okay, so this is the south. So magnetic field lines go like this. And you have a wire in this direction. I mean, you can see it here, okay, that moves up and down, okay, in this direction. So it cuts through the lines of the magnetic field pretty much, okay? So the magnetic field between the magnets is constant. When the wire is moved, up and down, it cuts through the magnetic field lines. And so an EMF is produced, is actually, okay, let's say generated, given by minus, okay, the EMF is equal to the change in flux over time, so minus B times dA over dt. And then what is the area that changes in this case? It's given by the length of the wire times the x direction. So to visualize this is the length of the wire. Sorry, let me use a different color. So let's use orange. So this is the length of the wire, okay? And the area that changes is given by L times X, because X moves in this direction. So L times X is pretty much a surface, okay? I hope you can see this. I hope it makes sense. It's a little bit of a difficult problem, so I have to admit. So the M generated is given by B times L, because L is constant, times dx over dt. And dx over dt is pretty much the velocity with which the wire goes up and down, okay? So let's write this down. Since x changes, it represents a velocity and hence a change in phi flux, which generates the electromotive force. Okay. The student his hands pretty much. So the student makes a closed loop. So current passes through the wire. So through the hands of the student pretty much, because he's holding the wire, okay? So the closed loop is formed by the hands of the student, okay? Because of the current, because of that current, the wire experiences a force F equal to B times the current times the length, okay? Due to Newton's third law, this magnetic force is also experienced by the magnets, and it's equal and opposite in nature. So the reading on the scales changes. So in this problem, you pretty much have to recognize that two things are going on. The first thing is that the motion of the wire up and down through the magnets cuts the line, cuts the magnetic field lines, creating a current, because this is a closed loop. Okay, so that current creates a magnetic field that is experienced by the magnets. Therefore, the reading of the scales changes. Okay, part B. Okay, a voltmeter was connected across the ends of a second wire. The student moved this wire vertically upwards between the magnets at a constant speed. A potential difference PD was observed on the voltmeter while the wire was moving. Calculate the maximum PD that could have been measured. And they give you the length and height of each magnet, the magnetic flux density, and the vertical speed. So, first of all, let's find the area, the maximum area, okay, that the wire can traverse. So X is 34 millimeters. So the area is 20 times 34 times 10 to the negative 6, because you have to convert to meters. So 6.8 times 10 to the negative 4 meters squared. Now the velocity is only is given by y over t. So time is y over v. So the maximum possible vertical distance is just 20 times 10 to the negative 3 over 2.2 meters per second. So the maximum time the wire can spend cutting the magnetic field lines is 9.1 times 10 to the negative 3 seconds. And since the electromagnetic force is minus d phi over dt, we will take the positive. D phi is b times a over time, pretty much, okay? B is 0.35, a is 6.8 times 10 to the negative 4 over 9.1 times 10 to the negative 3. So the maximum possible voltage is 0.026 volts. Okay, where we use the maximum possible change in flux, which is B times A, and then the maximum possible time, which is the time for the wire to go from all the way up to all the way down. Okay, so that's the answer. Question 16. A student was investigating capacitors and set up the circuit as shown. The student planned to use the circuit to measure the potential difference V across the capacitor C as it was charged and discharged through the resistor R. Give 2 reasons why the circuit did not operate as intended. So, okay, in the charging phase, the voltmeter is not connected to the capacitor at all. So that's one problem. So the voltmeter is not connected across the capacitor when charging. Okay, because I mean, if when charging the switch is over there, so the voltmeter is not connected at all. So that's the first problem. And if the switch Y is closed, so if we take the switch, sorry, if we move the switch to Y, okay, the capacitor is short circuited. So if we move the switch to Y, the capacitor is short circuited, and it won't discharge via the resistor. Okay, and that's the answer. Part B. The student moved the switch from position X to position Y at time t equal to 0. The student recorded values of V as t increased and plotted the graph shown. Let's see. From position X to Y. Okay. The capacitance of capacitor C was 2.2 microfarads. Determine the resistance in the circuit when the switch was at position Y. Okay, this is an interesting question. So I guess here it is assumed that you use a resistor after all, okay, which is not shown in that circuit. Anyway, so when a capacitor is discharging, V is V naught, e to the minus t over RC, which is the time constant. Here V naught is 6.2 volts. I mean, you can see it over here. It's 6.2, okay. And 0.37, so 37% of V naught is 2.3 volts. So 2.3 is somewhere, let me think, 2, 4, 6, so 2.3 is somewhere here, okay. So the initial voltage, which is 6.2, drops to 37% of that, which is 2.3 volts, after about 23 seconds. So tau, the time constant, which is equal to RC, is 23 seconds. So if we solve for R, we find 23 over 2.2 microfarads, which gives you 10.45 mega ohms. Okay, so that's a large resistor. Right, so question 2. Determine the average current in the circuit between 0 and 30 seconds. Okay, so C, the capacitance, is Q over V, right? So Q is CV. Then the current is Q over time, right? So Q is IT. So now the charge, let me think. So at time equal to 0 seconds, Q is C times V, which is 2.2 times 10 to the negative 6 times the voltage, which is 6.2. So the charge is 1.36 times 10 to the negative 5. Actually, I'm going to need a clean page for this problem. So 1.36 times 10 to the negative 5 coulombs at time equal to 30 seconds, which is easy to work with, okay? So at 30 seconds, the voltage is 1.8, okay? So Q prime is 2.2 times 10 to the negative 6 times 1.8. So the charge is 3.96 times 10 to the negative 6, negative 6 coulombs. Therefore, the average current, which is Q over T, let's say delta Q over delta T, is just 1.36 times 10 to the negative 5 minus 3.96 times 10 to the negative 6 over 30 seconds. This gives us 3.2 times 10 to the negative 7 amperes. And that's the answer. Okay, so they give us those times and we calculate things. Okay, good. Calculate the energy dissipated by the current in the circuit between 0 and 30 seconds. So, okay. So, the energy is given by 1/2 CV squared, okay? At 0 seconds, the energy dissipated is 1.2 times 2 times 2 times 10 to the negative 6 times the voltage squared, which is 6.2 squared, gives you 4.23 times 10 to the negative 5 joules. At 30 seconds, the energy dissipated is 1.2 times 2.2 times 10 to the negative 6 times 1.8 squared. This gives you 3.56 times 10 to the negative 6 joules. So delta W is the difference between these two, which is 3.87 times 10 to the negative 5 joules, where you subtract these from these pretty much, okay? Wow, this is a difficult paper, guys. So let me see. Question 17. In 1897, J.J. Thomson demonstrated that electrons are small negative particles. The diagram shows the apparatus used by Thomson. So we have this nice tube, okay. The potential difference V was applied across the metal plates. So here, so V was applied here, producing an electric field between them. A magnetic field of flux density B was applied at right angles to the electric field. So the electric field direction would be this. So the magnetic field was in this direction, okay? So these two would be perpendicular, something like that. Okay, let's move on. Let's keep reading. So electrons were emitted from the cathode and accelerated towards the anode. The electrons move between the metal plates with speed v. Thomson adjusted B until the electric and magnetic forces of the electrons were equal and opposite, so the electrons passed between the metal plates in a straight line. The plates are separated by distance d. Show that the speed v of the electrons is given by that expression over there. So we pretty much have to say that, okay, the magnetic force on the electrons, which is QVB, must equal the force experienced by the electric field, which is Q times E. And for parallel plates, we know that the electric field is equal to the voltage, which I'm gonna write like that to distinguish from this V, which is the velocity, okay? V over the distance between the plates, okay? So Q cancels actually, and the velocity is simply equal to, let me see, the voltage applied between the metal plates over the magnetic field applied in this direction, okay, or times distance. So this was a simple proof, actually, I think. Now, part 2. An experiment was carried out using similar apparatus. Show that the velocity was about 3 times 10 to the 7 meters per second. So this is a simple application of what we just found. So 231 volts over 5.5 times 10 to the negative 4 times 1.5 times 10 to the negative 2 to convert back to meters gives us 2.8 times 10 to the 7 meters per second, which is about 3 times 10 to the 7 meters per second. And here I want to make a brief pause and say that, okay, assume that you are not able to prove this, okay? You can still use it as given and grab 2 marks from this problem because you just apply the formula, okay? So, I mean, these are kind of, these are some techniques you can use in tests in general, okay? Yeah, so this is what I wanted to say. So, part 3, when the electric field between the plates is switched off, the electrons move in a circular path of radius 39 centimeters due to the magnetic field. The accepted value of the charge per unit mass of an electron is 1.8 times 10 to the 11 coulombs per kilogram. Deduce whether the charge per unit mass of an electron calculated using data from this experiment is consistent with the accepted value. Okay, so when the electric field is switched off, the only force that remains is QVB. And in fact, this force is going to be perpendicular to the direction of motion. Therefore, we're going to have circular motion. So therefore, this force is going to play the role of a centripetal force, and it's going to be equal to mv squared over r. So this v cancels, and we can solve for q over m, which is charge over mass, and find that it's equal to v, the velocity, over the radius times b. So the charge of an electron is E over m of an electron. The velocity is 2.8 times 10 to the 7, which is what we calculated earlier, over 0.39 for the radius times 5.5 times 10 to the negative 4. And this gives us 1.31 times 10 to the 11 coulombs per kilogram. The difference is 1.8 minus 1.31 over 1.8 times 100. It's 27.2%. That's a huge difference. So our values are not consistent. That sounded poetic. So yes, let's move on. Part B. In 1927, J.J. Thomson's son directed beams of electrons at thin films of metal. The photograph shows one of the patterns observed. Explain how this pattern changed scientists' understanding about the nature of electrons. So this is diffraction, okay? So diffraction patterns are observed, which are similar to waves. Okay, so electrons must have a wavelength, therefore they undergo diffraction. Okay, so electrons behave as waves. So if electrons were just particles, you would never see something like this. So this is a diffraction pattern that's only observed in wave phenomena. So if you observe that same phenomenon in electrons, it means that electrons are also waves. So this is the answer. So let's move on. Question 18. In 1977, a fifth quark named the bottom quark was observed by particle physicists. The table shows the particles in the standard model known at that time. So they have the quarks and the leptons. Explain why the existence of a sixth quark was predicted. So the answer is that the standard model, let's call it SM, is symmetric. So for the up quark, you have the down quark. For the S quark, you have the charm quark. So for the bottom quark, you must have the top quark to kind of balance the standard model. And also, okay, I mean, I don't know if it's going to be asked later, but you also need a tau neutrino. So let's move on. A short time after formation, most quarks combine to make particles known as hadrons. There are two categories of hadrons. Name the two categories of hadrons. So these are baryons consisting of 3 quarks or 3 antiquarks. Okay, and mesons that consist of quark and antiquark pairs. Okay, part B. In 1995, the sixth quark, known as the top quark, was discovered using the Tevatron Collider at Fermilab. Fermilab is in Chicago, guys. There was a time in my life when I lived in Chicago and also near Chicago, so it brings memories. Anyway, a collision of a proton with an antiproton produced the top quark and a top antiquark. Particle experiments may direct beams of particles at stationary targets or collide beams of particles traveling in opposite directions. Explain the advantage of colliding beams of particles. So, one advantage is that you have zero momentum. So after the collision, products don't have a lot of kinetic energy. And no resultant momentum. Most energy is used to create particles. Okay, so what I'm trying to say is that since you have two beams coming in opposite directions, the total momentum is zero, okay? So all the energy is used to produce particles, whereas if you have a head-on collision with a stationary target, lots of energy is gonna get lost in the collision and stuff like that, okay? Okay, so massive particles can be produced. Now, question 2. In the collider experiment, the protons and antiprotons each had total energy of 900 GeV. Calculate the maximum kinetic energy in joules of a top quark produced in this experiment. And the rest energy of top quark is 173 GeVs. So the total energy is equal to the kinetic energy plus the rest energy, okay? So the kinetic energy is equal to 900 GeV, which is the total energy, minus 173, which is the rest energy. So the kinetic energy is 727 GeVs, which is equal to 1.16 times 10 to the negative 7 joules. So that's the maximum kinetic energy. Because the total energy in relativity is equal to the kinetic energy plus the rest energy, okay? So, and the rest energy, by the way, is the infamous mc squared, okay? And that's the answer. Part 3. Deduce whether a top quark with kinetic energy 1.2 times 10 to the negative 7 is traveling at a relativistic speed. So the kinetic energy, we can convert that kinetic energy into EVs. So the kinetic energy is 1.2 times 10 to the negative 7 joules. And if we divide by 1.6 times 10 to the negative 19, and I will need my calculator, which I don't see. So the kinetic energy ends up being 750 GeVs, which is much, much larger than the rest mass, than the rest energy, which is 173 GeVs. So yes, it's relativistic. Okay. And when we say relativistic, we mean something that has an energy which is much larger than the rest mass. Okay. So most types of quark form hadrons on a time scale of 10 to the negative 23 seconds. The top quark does not form hadrons because its lifetime is only 10 to the negative 25 seconds. A student suggests that if the top quarks traveled at relativistic speeds, it could be possible for them to form hadrons. Assess the suggestion. So, okay, so the suggestion is wrong pretty much, okay? So from the observer's point of view, the lifetime would increase due to time dilation, but as far as the T quark is concerned, from its point of view, the lifetime is still 10 to the negative 25 seconds. So no hadrons can be formed. All right, and this is it. This was a really difficult test, guys. So I'm gonna try to edit it and make it look good. But I hope this helps, and let me know what you think about the solutions in the comments. Okay, and this is it.